Let's just start with stabilization. First of all, the word soil stabilizer implies that you're trying to stabilize the soil, that you're trying to improve its ability to not move and shift around on you or shrink and swell. And right off the top, we are not even a soil stabilizer. We would refer to our product as an accelerated lithification technology. And we'll basically, in essence, what we are doing is changing the soil at the molecular level, not gluing it together, not making it sticky, but actually forming new aluminum and silica chains and changing the structure at the molecular level as opposed to trying to stabilize the soil. So everybody's familiar with base course. Base course is the standard under roads. It's also standard on county roads that don't have a surface. And again, it's a fractured rock and sand that are compacted. And when used under an asphalt surface, for example, the quality of a base course is dependent upon the gradation of the material that has been crushed. So, for example, in the sub-base, typically they're looking for a minimum of a 40 CBR and 1.5 inch minus fractured aggregate. And as you get into the base layer, 3/4 inch minus. And typically that's in the 70 to 80 CBR, CBR standing for California bearing ratio. And there are about 5 different kinds of ways of measuring the strength. California bearing ratio is one, Texas triaxial, R value, unconfined compressive strength, and resilient modulus. And the resilient modulus is really the most expensive, most reliable, and really the one that most of the DOTs are relying on for measuring that strength. Base course will have 25,000 PSI to 35,000 PSI modulus as measured in resilient modulus. And that scale is called a nomograph scale, and it maxes out at 70,000 PSI modulus. They never see base course that gets that high, but the scale can measure up to 70,000 PSI modulus. Now that's for an unbound material, meaning concrete is bound, Lithtech is bound. So when you get into measuring resilient modulus in a bound material, you can go over 2 million PSI modulus. So when we treat base course, for example, with Lithtech, we will take it from 25,000 PSI modulus. We can go over 2.3 million PSI modulus, but it's overkill. It becomes more expensive than your budget probably, and it's just not necessary. Where we find as our target is 500,000 PSI modulus. And the reason that we arrived at that number is we have an engineer who was one of the top engineers for ADOT, Arizona DOT. He's now the lead engineer for Fisher Industries. He did a white paper study on lithified technologies and said that when you achieve 500,000 PSI modulus, you are now the equivalent structural coefficient, sometimes referred to as just a structural number, of asphalt. So when a road is being designed and they are trying to achieve certain load-bearing capacity, oftentimes measured in California Traffic Index, other places in the country it's ESALS, ESALS, and that's equivalent single axle loads. So when they design a road that needs to have X million ESALS for a 20-year design, the structural number to achieve that is generally found in the thickness of the asphalt, because base course has a cap of what they will allow to be in the design of the road. There's only so much strength that you can achieve in base course, so all of that strength is moved to the surface. Well, with Lithtech and through value engineering, a new possibility exists. Because we can reach the same structural coefficient or the same structural number in your foundation by treating the base and achieving 500,000 PSI modulus, let's say that we treat 8 inches of base course. That is now the same as building your road on top of 8 inches of asphalt. That means you can reduce the pavement design from, say, 4 to 6 inches down to 1.5 or 2 inches, whatever the minimum is the laydown machine can put down on top of that road. And you just saved 50 to 67% of the cost of the asphalt. And the asphalt is the biggest number in the total cost of building a road. This is what we're bringing to counties, is the possibility on rural roads to now put chip seal on top of a Lithification treated base course. And now you're putting chip seal on the equivalent of asphalt. And chip seal on top of base course is not the greatest idea, because first of all, it's only about an inch thick and you're on a foundation that can shift and move on you, and that road can come apart. But when you put it on top of a bound and non-dispersive foundation, meaning you can take a core sample of Lithification, put it underwater indefinitely, and it's not going to come apart. So the two things that we are bringing to the equation is extreme load-bearing capacity and water resistance. When you look at soil stabilizers, there's a gentleman that I've met with in New Mexico that he just retired after 30 years with the New Mexico DOT, head of the product evaluation program. And he told me, Bob, I've tested all of the soil stabilizers, and frankly, we've never seen one make it a year. And they look at them as short-lived snake oil, if you will, and they leave a trail of dissatisfied customers. And because the market is so large, they just go on to the next one, and they don't care if it fails, and they'll just continue to go on to the next one. Going down the list, I'll speak to what each of these are and what their strengths and downsides are. But the SPP's sulfonated petroleum product is a sulfuric acid-based product. Again, it's a byproduct that comes out of oil refining, and is what's left over. And its downside is twofold. One is when you put it into a high pH soil, you're neutralizing the acidity, and the alkalinity neutralizes its capacity to do anything. Put it into a acidic soil, you have the best chance of it working, and it must have a minimum of 15 to 20% clay content, and that clay content has to have a certain amount of cation exchange capacity exchange to make it hard. And I have seen roads with this material that are extremely hard. And in fact, when we first started looking into this industry, we looked at a company out of Canada, had a product called Road Packer, and I thought this was going to be the answer. And this road was extremely hard until it rained, and then it was just mud. It's water soluble, which most of these are. All of these, by the way, with the exception of lime and cement, are liquid. That in itself has its limitations. The biggest limitation with a liquid, and I know this from our firsthand experience, is we started out as a liquid, and we were putting in as much raw materials into that liquid as possible, but 50% of the formula was water, even in its most condensed form. And when we were putting in a 3% dosage into the soil, only 1.5% of it was actually active ingredients. 1.5% of it was water. And all of these things that are in a liquid form must go in at optimum moisture content. There is a bell curve in a Proctor that when you are too dry, you're not getting the proper bonding, and it's just not achieving the maximum strength. And when you get too wet, now the soil is pumping and you're losing strength that way. So you've got to be in at the top of the bell curve. Well, you can't get enough raw materials, frankly, in a liquid to get the reaction that you need in the soil. And that is one of the biggest downsides to all liquids. Enzymes, also a liquid, and these are live organisms that eat and excrete and make things sticky. And ultimately, all of these things I would refer to as a compaction aid, as opposed to actually getting a long-lasting strength and keeping the water out. Polymers are a dirt glue. It even looks like Elmer's glue. So now you're trying to glue the dirt together. And it has two downsides. It breaks down with UV light, and it's very brittle in cold temperatures. There's only so much a glue can do. When a 40-ton truck drives over the top of it, it's going to break those bonds. And that's what's happening continually, is bonds are getting broken and they're never going to get reconnected. Lignosulfinate, sometimes called lignin, this is a byproduct of processing paper. They discovered lignins in the early 1900s in the manufacturing, in the paper mills. It was a byproduct that was left over, and it's a dark brown molasses looking thing. A lot of times people refer to it as tree molasses. Again, lignins require a certain amount of clay content. They used to take this leftover byproduct in processing paper and just dump it into the rivers. And they were killing all the fish and the smell and all that stuff. And the EPA stepped in and said, you can't do this anymore. And they're like, what are we going to do with it? So they just started to spread it on roads. And in some roads, it got really hard. In some roads, it didn't have any impact at all. And it turned out it had to have a certain amount of clay and a certain amount of cation exchange capacity. Again, this is one of the products that we looked at in our early days called road bond. And it got really hard until it rained, and then it was all mud. Magnesium chloride, magnesium, sodium, and calcium chloride, all of these things are forms of salt. And they're really not a soil stabilizer. They're more of a dust suppressant. They are hydrophilic in nature, meaning they attract water. The way they work is in a humid climate that doesn't rain. That in itself is a challenge to find, but that's the ideal scenario for magnesium chloride. It is sprayed onto the roads, and it will pull the humidity, the moisture in the air, and hold it into the road. So the road is dark in color, looks like it's been watered, and it keeps the dust down. The downside is it's hydrophilic. It attracts water. The last thing you want to put in a road is something that attracts water. You want water to be repelled, because it's in the top two reasons that roads fail: weight loads and water. And so they say with magnesium chloride, it will last a maximum of 6 months or until the first good rain, and then it washes out. It also kills the plants. And they did a project near where I live with magnesium chloride, and they had to send notice out to all the homeowners to not walk your dogs on it during the early stages of it, because it'll burn their paws and so forth. Molasses and sugars, again, they're just making things sticky. They're more of there are even shredded up and recycled tires that have been tried. Fly ash, which is a byproduct of coal. And the fly ash takes a large amount of product going into it to get a reaction. And it can make things really hard. It's not used so much today, both environmentally, and the cement industry buys it up and puts it into the cement. It was something, years ago that was used. Lime and cement are the two things that are the standards in the road stabilization industry and DOTs and so forth. Lime goes into high clay content soils, and cement goes into sand. So with cement, the ideal is when there is 6% or less clay content, it will be used in sandy soils. They will use it sometimes up to 10% clay content, but the higher the clay content, the less effective that it is. And so it's a window of just the sandy soils. Conversely, lime is used primarily when you're 20% clay or higher. 20 to 50 PI, plasticity index, is typically where lime is used. Once you get over a 50% PI, it's generally export time. They don't even try to stabilize it. Now, the downside with lime is it will stiffen the soil, and it typically will not get over 160 PSI unconfined compressive strength. And Lawast is the largest lime producer in the world, and that's their target, is just to achieve 160 psi unconfined compressive strength, and then put some kind of surface over it as fast as you can to try to keep the water out. The other downside with lime, Dennis Seal put behind his name as an engineer and went through the ranks of Caltrans and then TxDOT and all the way through the top as far as he could go in TxDOT, and then a principal of Kimley Horn, and now a consultant with Pap Dawson. But anyway, he said he's been around long enough that he's gone back to projects that they did 10 years ago where they put in a ton of lime and there's no evidence that any lime ever was put in there. It just kind of returns back to the soil that it was to begin with. So over time just kind of disintegrates and goes away. So that really is the background on the different soil stabilizers, about how we're different.